Hi students, today we are going to discuss the topic Lamberts Law and Monochromators in analytical instrumentation. Today we are going to deal with Lamberts Law and Monochromators. The learning objectives of today's session: upon completion of this presentation, you will be able to understand what is Lamberts Law. What are monochromators? What are the types of monochromators? In the various types of monochromators, you are going to study about prism monochromators. Upon completion of this presentation, you will be able to understand Lamberts Law, monochromators, types of monochromators, and prism monochromator. Lamberts Law. It is one of the laws of photometry. It is a combination of two laws. It consists of Lamberts Law and Beer's Law. Lamberts Law states that each layer of equal thickness of an absorbing medium absorbs an equal fraction of the radiant energy that traverses it. Let us take the medium. If you are going to take a medium and allow the radiation to pass through this medium, according to Lambert's law, it states that each layer of equal thickness of an absorbing medium absorbs an equal fraction of the radiant energy and transfers it. Lambert's law is expressed as transmittance T is equal to I by I naught, where I is the incident radiant energy, I naught is the incident radiant energy, and the I is the energy which is being transmitted, and absorptions is equal to logarithm of 1 by T, where T's law states that each layer of equal thickness of an absorbing medium absorbs an equal fraction of their radiant energy that traverses it. This is called Lambert's law. Then coming to the second law of photometry, that is Beer's law, it states that absorption of light is directly proportional to both the concentration of the absorbing medium and thickness of the medium in the path. Beer's law states that absorption of light is directly proportional to both concentration of the absorbing medium and the thickness of the medium in the light path. Based on this, for a fixed path length, absorption spectroscopy can be used to determine the concentration of the absorber in a solution. So, absorption spectroscopy. So, Beer's law and Lambert's law, they are two different laws. The Lambert law, it states that each layer of equal thickness of an absorbing medium absorbs an equal fraction of the radiant energy. Whereas when we come to the case of Beer's law, it states that the absorption of light is directly proportional to both concentration of the absorbing medium and the thickness of the medium in the light path. Based on this, for a fixed path length, absorption spectroscopy can be used to determine the concentration of the absorber in a solution. So, now coming to the combination of these two laws, we have Lambert's law. It states that there exists a linear relationship between absorbance, that is nothing but the amount of monochromatic radiant energy absorbed or transmitted by the solution, and the concentration of an absorber present in the path of the electromagnetic radiation. It is both these two laws. It states that there exists a linear relationship between the absorbance, that is the amount of monochromatic radiant energy absorbed or transmitted by a solution, and the concentration of an absorber present in the path of the electromagnetic radiation. So, there exists a linear relationship between absorbance and the concentration. Absorbance of the monochromatic radiation and concentration of the absorber. It depends on the concentration of the absorber. Okay, so when we are asked to state what is Lamberts law, it states that there exists a linear relationship between absorbance, the amount of monochromatic radiant energy absorbed or transmitted by a solution, and concentration of the absorber present in the path of the electromagnetic radiation. It states that there exists a linear relationship between absorbance and concentration of the absorber present in the path of the electromagnetic radiation. So, Lamberts law can be represented by an equation A is equal to small a BC, where capital A is the absorbance, A is the absorptivity, it is a constant, okay, and B is the path length of the sample, that is the path length of the cuvette in which the sample is contained, and C is the concentration of the compound in the solution. Okay, once again I would like to specify the equation. A is the absorbance. Absorbance is given by the relations A is equal to, capital A is equal to small a into B into C, ABC it is called, where capital A is absorbance. It is the absorbance of the solution. It is proportional to concentration C. So when we equate it, when A is proportional to C, A is some constant into C. What is that constant? That constant A, small a, is called the absorptivity of the, it is nothing but the absorptivity of the medium. B is the path length of the sample, that is the path length of the cuvette in which the sample is contained, and C is the concentration of the solution. C is the concentration of the solution. So once again, what is Lamberts law states? There exists a linear relationship between absorbance and concentration of the absorber present in the path of the electromagnetic radiation. So there exists a linear relationship. A linear relationship exists between the absorbance of the solution and the concentration of the solution. Absorbance of the radiation and the concentration of the solution present in the path of the electromagnetic radiation. Okay. So the next slide, you are going to see the here you are having the media in between, the absorber. Your media is placed in between, and radiation is incident on this media. It is incident radiation. The incident radiation, the monochromatic radiation, is made to fall on the medium, on the material or the sample in which you are going to measure the concentration of the sample. When this radiation is incident on this medium, then what is happening? Some of the radiation is getting reflected back, some is being transmitted, and some is being scattered, and you have some other effects like fluorescence is taking place. So you have in the center the medium. What is happening when monochromatic radiation is falling on this medium? Some of the radiation which is falling on the medium, it is getting reflected back. Some of it is being absorbed. When you see the picture in the middle, you can observe some of the radiation is being absorbed, and you have some of the radiation being transmitted. And this transmitted radiation, it can be either scattered, or you can observe the effects of light like fluorescence, phosphorescence, you can observe. Okay, so this is happening to the interaction of matter with the radiation. When radiation falls on the matter or the sample, monochromatic radiation, when it falls on the sample, what happens? The sample will undergo the incident radiation, will be some of the radiation will be reflected back without passing into the sample. Some of the radiation will be absorbed into the medium and the remaining part is being transmitted. The transmitted radiation, it can be either scattered or it can be either scattered or it can be you have the effects, you can observe the effects like fluorescence and phosphorescence. So what is the equation when we observe the equation? When we observe the equation of interaction of radiation with matter, we have A is absorbance, that is nothing but equal to small a b c, where A is the absorbance, small a is the absorbivity of the medium, B is the path length of the sample and C is the concentration of the compound in the solution. So this is the basic equation which is being observed by Lamberts law. Then we have the other, there exists a relationship between absorbance and transmittance. There exists a relationship between absorbance and transmittance. What does this relationship states? So the relation is transmittance with transmittance. What happens here? Transmittance, when we are taking transmittance and absorbance on the x-axis, you can observe the absorbance rate is changing and the transmittance, percentage of transmittance is also changing. For different values of absorbance, we have different values of transmittance. For different values of absorbance, we have different values of transmittance. See in this next slide, you can observe. If all the light passes through the solution without any absorption, then absorbance is 0. Is it not? The material is not able to absorb any amount of radiation falling on it. Then what is the result of that? The result of that is there is no absorbance. The absorbance is absolutely 0. When the absorbance is 0, the transmittance is 100%. Is it not? Transmittance is ability to give off something, that is called transmittance. So if all the light that is passing through the solution or through the media, if it is being passed off without any absorption, then the absorption is 0. Absorbance is 0 and its percentage transmittance is 100%. So there is a relationship between absorbance and transmittance. Absorbance A is equal to logarithm of 1 by percentage of T. So it is inverse 1 by percentage of T. Percentage of T is transmittance. If all the light is being absorbed, then transmittance is 0 and absorption is infinity. Okay. So once again, when we see the picture here, in your figure there, transmittance versus absorbance figure, what you have understood? You have understood the percentage of transmittance is ranging from 0 to 100 with a variation of 10% for each step, 0 to 10, 10 to 20, 20 to 30, so on, from 90 to 100. There is a step of 10% for each instance. Then when we observe the absorbance relationship, as you know, absorbance A is equal to logarithm of 1 by percentage T, 1 by percentage T. So when we are plotting for different values of transmittance percentage in that formula, A is equal to logarithm of 1 by percentage T to the base 10, you get different values of absorbance. And those whether you cannot measure that absorbance. When absorbance is when transmittance is 10%, then you have different value of absorbance. Okay, 1 by 10, 10 power minus 1. So negative side you are getting the values -1. Okay, then if the transmittance is 20, then when you are using that relation, A is equal to logarithm of 1 by percentage t, 1 by percentage t, 1 by 20. When you are calculating the value of A, you get it as 0.7. When transmittance is 30%, you're getting another value. When transmittance is 40%, you're getting 0.4. When transmittance is 50%, you're getting absorbance as 0.3, and so on. When transmittance is 100%, that means absorbance is 0. Why it is 0? Because your total radiation is being transmitted off. No radiation is being absorbed by the material there. Then its transmittance is 100%. So have you understood the relationship between absorbance and transmittance? There is a relationship which exists between absorbance and transmittance that is given by the formula A is equal to logarithm to the base 10 1 by percentage of t. When you substitute the value of t, different percentages ranging from 0 to 100, you will get the values, corresponding values of absorbance. When you plot the values of absorbance, you will get the graph as shown in the figure there. Okay, so if all the light passes through the solution without any absorption, then absorbance is 0 and percentage transmittance is 100%. Okay, percentage transmittance is 100%. If all the light is being absorbed, then percentage transmittance will be 0. Okay, if all the light is absorbed, then there is no transmittance. Then what will be the percentage of transmittance? It is 0. Then absorbance is infinite. Absorbance is infinite. So in the intermediate values, the extreme between these two extremes, that is when the transmittance is 0 and when the transmittance is 100, you can plot the graph and you get the graph as shown in the figure. So have you understood what is the relationship that exists between absorbance and transmittance? So the relationship between absorbance and transmittance is logarithm of A is equal to logarithm of 1 by percentage t to the base 10. Okay, have you understood the importance of calculating the percentage transmittance and absorbance? So if all the light that passes through the solution without any absorption is transmitted, then absorbance becomes 0 and percentage transmittance becomes 100%. And if all the light is absorbed, then percentage transmittance is 0 and absorption is infinity. Okay, so when we go to the next slide, so the next slide, we are calculating we are plotting a graph between percentage transmittance versus path length. As I told you, even it depends on the transmittance rate, also depends on the length, the path length of the medium. It depends on the path length. Okay, how much material through which it travels. So there exists a relationship between percentage transmittance and path length. When you are plotting the values of percentage transmittance and path length, it is being observed that there is an exponential decreasing curve with path length. When the path length is more, that means path length is less, the transmittance will be more. When the path length is more, the transmittance will be less. That is all well known fact. When the length of if a radiation is being incident in a material or a medium, when the thickness of the material is more, the transmittance will be, when the thickness is more, the transmittance will be less. Okay, when the thickness is more absorption takes place. When more absorption takes place, what happens? The transmittance becomes less. Have you understood the relationship between percentage transmittance and path length? Path length is nothing but the length of the thickness of the material through which your radiation is being passed through. When the radiation is passing through a thicker material, what happens? The radiation will be absorbed by the material, and very less amount will be transmitted back. So when the absorbance is more, transmittance becomes minimum. When will be the absorbance more? When the path length is more. So when we are plotting the graph, taking path length on x-axis and percentage transmittance on y-axis, we are having an exponentially decreasing curve. When you are taking the transmittance as 100%, what is the absorbance? When the transmittance is 100%, absorbance is 0. When will the absorbance be 0? When the material thickness is very, very negligible, very, very small. When the material is very, very thin or very, very negligible, what happens? Very less amount of the material will be absorbed by the medium, and totally the entire radiation that is falling on the material will be transmitted off. So you are having when the path length is 0, the percentage is transmittance is maximum. When the path length is slowly increasing, your transmittance percentage is slowly decreasing, because when the length is increasing, absorption is also increasing. When the absorption is increasing, the transmittance is automatically decreases off. So have you understood how to plot that percentage transmittance versus path length curve? So when you are taking the path length on the x-axis and the transmittance on the y-axis, with the increase of path length, the transmittance decreases. So the next one is plot characteristic. In other words, we can say it is the absorbance versus path length. As I told you already, there is a linear relationship between absorbance and path length. Why? Path length increases, absorbance increases. Path length decreases, absorbance decreases. So you are having a linear graph there. When you are plotting a graph between absorbance and path length, when you are taking the path length on the x-axis and the absorbance on the y-axis, what happens with increase of path length? Path length is nothing but the material through which the medium, the thickness of the material of the medium. If the length of the medium is increasing, the incident radiation, when it falls on the medium, when more the thickness, more the absorbance. So you are having a linear graph there. You are taking on the x-axis path length, you are taking on the y-axis the absorbance. When you are plotting a graph between path length on x-axis and absorbance on y-axis, you are getting what? You are getting a linear graph, which you can observe in the graph shown in the slide. Okay, shall we move to the next one? Next one is we are plotting a graph between absorbance and concentration. Absorbance and concentration. What happens if it is more concentrated? The more the concentration, the more the absorbance. The more the concentration, the more the absorbance. So concentration is linear up to a certain level. It is linear up to a certain level, and after that it begins to decrease. So absorbance versus concentration. When you are taking the concentration on x-axis and absorbance on y-axis, what happens? The concentration begins to increase. When the concentration is more, the absorbance is more. Okay, then coming to the next, that is we are having concentration on x-axis and absorbance on y-axis. The more the concentration, the more the absorption. Then coming to the limitations of Beer's law. Most important limitation is it is only applicable to monochromatic radiation. As I first told you in the definition of Lamberts law. What is the definition of Lamberts law? There exists a linear relationship between the concentration and the absorbance. Okay, so there exists a linear relationship. Before going into the limitations, I would like to tell you certain things. There are some prerequisites for Beer's law. There are some prerequisites. What are these prerequisites? Let me go to the first slide about Beer's law. When we are discussing about this law, I would like certain prerequisites of Beer's law. There are at least 6 conditions that need to be fulfilled for Beer's laws to be valid. For this law to be valid, you need 6 prerequisites. The prerequisites are nothing but 6 conditions which the law has to meet. The first one is the absorber must act independently to each other. The absorbers must act independently to each other. The absorbing medium must be homogeneous. It must be homogeneous in the interaction volume. Then the absorbing medium must not scatter the radiation, or it should not be, there must be no turbidity. Okay. The incident radiation should preferably be monochromatic or have at least a width that is narrower than that of the absorbing transition. Okay. So it must be preferably monochromatic in nature. That is the 4th one. Then the incident radiation must consist of parallel rays, each traversing the same length in the absorbing medium. You must consider 2 parallel rays. The rays must be parallel such that each are traversing the same path in the absorbing medium. Then the incident flux must not influence the atoms or molecules. It should only act as non-invasive probe of the species under study. Now you are taking the material which you are going to study. So it should not influence the atoms or the molecules, but it should not influence the atoms or the molecules. So these are the 6 prerequisites for the law to be valid. For the law to be valid, for the Beer's law to be valid, what are the 3 conditions? The first one is about the absorber. The absorber must act independently to each other. Then second one, the absorbing medium. Absorber must act independently to each other. The second one is the absorbing medium must be homogeneous in nature. The absorbing medium must be homogeneous in nature. Then third one, the absorbing medium must not scatter the radiation. No turbidity. Then the 4th one is the incident radiation should preferably be monochromatic. It should be monochromatic preferably. Then the incident radiation must consist of parallel rays of beam of rays, each traversing same length in the absorbing medium. And the 6th one, the incident flux must not influence the atoms or molecules. It should only act as a non-invasive probe of the species under test. So these are the prerequisites for the Beer's-Lamberts law to be valid. What does the law states? That there exists a linear relationship between absorbance and transmittance, and it states that concentration of the substance in solution is directly proportional to absorbance. Okay, there exists a linear relationship between absorbance and transmittance, and also it states that concentration of the substance in solutions is directly proportional to the absorbance. So coming to the limitations, when we come to the limitations, so limitations of Beer's law. The linearity of Beer's-Lamberts law is limited by, first and foremost thing is, we must remember that it is applicable to only monochromatic radiation. What is meant by monochromatic radiation? I was talking frequently about using this word monochromatic. Mono means single, chromo means color. Radiation with single color radiation is called monochromatic radiation. Okay, it is only applicable to monochromatic radiation. Now, then non-linearities also arises in high concentration solutions. Okay, so what are the first limitations? The linearity of the Beers-Lamberts law is limited by chemical and instrumental factors. It is being limited by chemical and instrumental factors. Causes of these non-linearities. Why the non-linearities arises are maybe due to deviation in the absorptivity quotient at higher concentrations. Okay, there is a deviation in the absorptivity quotient at higher concentrations. Then scattering of light due to particulates in sample. Suppose there are some particulates in the sample, the light gets scattered off. All the light will not be transmitted or absorbed. Okay, so one of the reason is Beers-Lamberts law is the linearity. First and fundamental limitation is it is only applicable to monochromatic radiation, and non-linearities arises at higher concentrations. Remember, non-linearities arises at higher concentration. Why these non-linearities arise? The non-linearities arise maybe due to what are the factors which affect the non-linearities is deviations in absorptivity coefficient at high concentrations where concentration is greater than 0.01 mole due to electrostatic interactions between molecules in close proximity, and scattering of light due to particulates in the sample. Scattering of light due to particulates in the sample. Then the other limitations are fluorescence or phosphorescence of the sample, then changes in the refractive index at high analyte concentration. When the concentration of the sample or the analytes are high, then there are changes in the refractive index of the sample. Then shift in the chemical equilibria as a function of concentration. Then non-monochromatic radiation. Okay, as I told you, the radiation must be monochromatic in nature. Monochromatic radiation deviations can be minimized by using a relatively flat part of the absorption spectrum, such as maximum of an absorption band. Then we have the stray light. The stray light also affects the absorption. So once again repeat limitations of Beers law, that is nothing but fluorescence or phosphorescence of the sample, changes in the refractive index at high analyte concentrations, shifts in the chemical equilibria as a function of concentration, non-monochromatic radiation deviations can be minimized by using a relatively flat part of the absorption spectrum, such as the maximum of the absorption band. And then we have the stray light. So coming to the next, so we are going to deal with monochromators. What is a monochromator? Monochromators are used to select the desired frequencies from a radiation source and reject the radiations of other frequencies. In short, I can tell you what is a monochromator. A monochromator is nothing but a device which is used to isolate a narrow band of wavelengths. It is a device, optical device I can say, which is used to isolate a narrow band of wavelengths. For that purpose we are using monochromators. They are used for isolation. Monochromators are used to select the desired frequencies from the radiation source and reject the radiations of other frequencies. Suppose you have a radiation source. A source radiates the energy. Suppose you want a specific radiation with specific frequency, use monochromator. So monochromator is used to isolate a narrow band of radiation, narrow band of wavelengths. Okay, a monochromatic module, it consists of, we'll see what are the modules it consists of. It consists of an entrance slit, it consists of an collimator, it consists of a grating, it consists of different components of a monochromator we'll be seeing. But what is the main purpose of the primary function of a monochromator? The primary function of a monochromator is to provide a beam of radiant energy. It is used to provide a beam of radiant energy of given nominal wavelength and spectral bandwidth. It is used to provide, the primary function of a monochromator is to provide a beam of radiant energy of a given nominal wavelength and spectral bandwidth. It is nothing but a device which is used to isolate the radiation of specific wavelength or frequency. In other words, you want a desired frequency or desired wavelength of the radiation, then you can use a monochromator. So its primary function is to provide a beam of radiant energy of given nominal wavelength and spectral bandwidth. Okay. So the performance of a monochromator depends on three factors. A monochromator must possess three characteristics. It must possess three characteristics. What is that? It must possess good resolution. It must gather the light gathering power. It must have the light gathering power, and then the purity of the light output. Okay, the purity of the light output. What is meant by the resolution? It depends on the dispersion and on the perfection of the image formation. Resolution, it depends on the dispersion and on the perfection of image formation. Then the second one is, it must gather, light gathering power must be there more for a monochromator. And the third thing is purity of light output, which can be determined mainly by the amount of stray or scattered light. Purity of light determined mainly by the amount of stray or scattered light. Large dispersion and high resolving power in monochromators are necessary. Monochromators must have large dispersion and high resolving power necessary to measure accurately emission spectra. To measure accurately emission spectra, it must have large dispersion and high resolving power. So the monochromators are classified into two types. They are classified into two types. What are they? First one is prism monochromator and the second one is grating monochromator. Prism monochromator and grating monochromator. What is prism monochromator and what is grating monochromator? We will discuss in detail in the forthcoming classes. Monochromators, how many types they are? What is a monochromator? It is a device which is used to select the desired frequency from the radiation of radiation source and reject the radiations of other frequencies. Whatever the desired frequency we want, it will select that radiation, that frequency, and it will reject other radiations of other frequencies. So we have two types of monochromators. They are prism monochromators and grating. In the grating we have again two types, diffraction grating and holographic grating. What are the two types? Diffraction grating and holographic grating. So what are the components of monochromators? Components of monochromators are the entrance slit. Then we have 5 parts. This monochromator has 5 parts. What are they? Entrance slit, collimating element, prism or grating as dispersing element, focusing elements and exit slit. Okay. So we have 5 types: entrance slit, collimating element, prism or grating as dispersing element and focusing elements and exit slit. So the 5 components of a monochromator are: first one is the entrance slit, second collimating lens, the collimating element, it may be a lens or a mirror. Third one is the prism, the dispersing element. What is the dispersing element? We have 2 types, the prism and the grating. Grating are the two dispersing elements are prism or grating. So you have the first one is the entrance slit, second one is the collimating element, third one is the prism or grating, fourth one is the focusing element. You are going to use lens or mirrors there, and fifth one is the exit slit. Fifth one is the exit slit. So what is the entrance slit? An entrance slit provides a narrow optical image. It provides a narrow optical image of the radiation source. It provides a narrow optical image of the radiation source. Then the second one is the collimator. What does the collimator do? It renders the light spreading from the entrance slit parallel. It makes the light from the entrance slit. The entrance slit, what does it do? It provides a narrow optical image of the radiation source. A narrow optical image of the radiation source is provided by the entrance slit. What is the next one? The next one is a collimator. The collimator renders the light spreading from the entrance slit parallel. It makes the light coming from the entrance slit parallel. That is the use of the collimator. Then the next one is the prism or the grating. It is the dispersing media, dispersing elements which disperse the incident radiation. What do? They disperse the incident radiation. Then the next one is the focusing elements. Again, you are going to use a collimator to reform the images of the entrance slit. Then the exit slit. The exit slit is again used to isolate the desired spectral band. Whatever the desired radiation or desired spectral band which you receive, that will be the desired spectral band will be isolated by the exit slit. So we have the entrance slit, we have the collimating elements, we have the prism or grating, and we have the focusing elements, and then the exit slit. These are the components of Then your next slide is prism monochromators. In the prism monochromator, in the figure shown here, you can observe the components of the monochromators. There are the 5 components. The first one is the entrance slit. Can you observe the figure there? You have an entrance slit. What is the purpose of the entrance slit? It provides a narrow image of the radiation source. It has a small aperture there. You can observe in the figure, the entrance slit has a very small aperture. So it provides a narrow optical image of the radiation source. Then the next one is the collimating lens you are using. You are using a lens there. The lens renders the light to spread parallel. See there, the light is entering from the entrance slit. It is falling on the collimating lens. What does the collimating lens do? It is making your ray to come parallel. Okay, and this parallel ray is falling on the dispersive media, dispersive element. Now the name of this monochromator is prism monochromator. So when it is said to be prism monochromator, you are going to use prism as the dispersive media. So the parallel light is made to focus on the prism monochromator. Then after dispersion in the prism, you are going to get another set of parallel rays. These rays go and fall on the next set. What is that? Is focusing lens. Okay. When they fall on the focusing lens will make your ray or make your radiation of desired wavelength fall on the exit slit, focus on the exit slit. What does the exit slit do? The exit slit isolates the desired spectral band. It isolates the desired spectral band. So this is the construction of a prism monochromator, where prism is used as dispersive medium. So isolation of different wavelengths in prism monochromator depends upon the refractive index of the materials. Okay. So what is isolation? This separation, isolation is nothing but separation of different wavelengths in prism monochromators depends upon the refractive index of the materials, which is different for radiations of different wavelengths. If you have like if you take an example of white light, that is visible light, it has 7 different types of colors. Okay, each color of light has its own wavelength. So what is happening here? The refractive index depends upon the wavelength of the radiation. Okay, depends upon the refractive index of the material, which is different for radiations of different wavelength. If a parallel beam of radiation, it is made to fall on the prism, radiation of two different wavelengths will be bent through different angles. As you know the principle of refraction, you will be observing the ray to be bending. That is, the bending action is called refraction. Okay. If the parallel beam of radiation falls on the prism, the radiation of the two different wavelengths will be bent through different angles. The greater the difference between these angles, the easier it is to isolate. If the bending is more, that means the bending between the two radiations is more. That means if the wavelength difference is more, you can isolate the wavelengths easily. This becomes an important consideration for selection of material for the prism. So you need to select the material such that the material with which dispersive medium is made, that must be considered when you are designing, when you are using a prism monochromata. This becomes an important consideration for selection of the material for the prism, because only those materials are selected whose refractive index changes sharply. Light from the source, what is happening in that figure we have seen, is made to fall on the prism. Let me show you the figure once again. Prism monochromata. So here is the figure. What you are doing in this prism monochromata, light from the source is made into a parallel beam and made to fall on the prism. By using a collimating lens, you can make the light fall from the radiation source when it is passing through the entrance slit, and using the collimating lens, it is made parallel. The light is made parallel and it falls on the prism. The entrance slit is at the focal point of the lens. Remember, the entrance slit is at the focal point of the lens, because we are using a convex lens here. Plano-convex lens is used here. So what is happening? Convex lens, so it's a focusing lens. So when any object is placed at the focal point of the lens, what happens? The output ray will be made parallel. So that principle is used here. So you are using the entrance slit. Where you are placing the entrance slit? The entrance slit is placed at the focal point of the lens. It is placed at the focal point of the lens. Then the prism disperses the light and photons of different wavelengths are deflected at different angles. Okay. So if the dispersed beam is refocused, the focal point from photons of one wavelength will be displaced from that of the different wavelength. So different wavelengths light, when we are passing, they will be deflected in a different way. This light of one wavelength can be selected by moving the slit across the focal plane. When you are moving the entrance slit, exit slit across the focal plane of the focusing lens, you can observe the different wavelengths or band of frequencies or wavelengths. The required wavelength is passes through the slit. The other wavelengths are blocked, because the exit slit has a narrow opening. Whichever wavelength you want to pass, when you are moving the exit slit, your radiation goes and falls on the exit slit. That specific spectral wavelength will be passing into the exit slit. So the materials commonly that are used for making this prism monochromators are made of glass or quartz. You are using glass prisms and quartz prisms. Glass prisms are best suited for visible region, and then quartz prisms, you are using glass prisms, you are using quartz prisms. Quartz prisms are glass prisms are suitable for visible region, whereas quartz prisms can cover the entire UV spectrum. Quartz prisms you are using for ultraviolet region. Prisms must be carefully polished and optically flat. Some care must be taken when designing the prism. Okay, prisms are made of either glass or quartz. Glass prisms are used for best suitable for visible region, and quartz prisms are best suitable for ultraviolet region. and these prisms must be carefully polished and optically flat. So to summarize our topic of discussion, Lamberts Law. Lamberts Law states that there exists a linear relationship between absorbance and the amount of monochromatic radiant energy absorbed or transmitted by the solution and the concentration of the absorber present in the path of electromagnetic radiation. The Lamberts law states that there exists a linear relationship between the absorbance and the concentration of the absorber present in the path of the electromagnetic radiation. Then we have studied about monochromators. Monochromators are used to select the desired frequencies source and reject the radiations of other frequencies. So we have studied about the different types of monochromators. Different types of what are the components of the monochromators we have studied. We have studied about the entrance slit. We have studied about the collimating elements, that is the lens or the mirrors we have used. Then we have studied about prism or grating as dispersing elements. Then we have studied about focusing elements, then the exit slit. The components of the monochromators. There are 5 components. What are they? The entrance slit, the collimating lens, the prism or grating, then we have the focusing elements and the exit slit. Then we have studied about the types of monochromators. There are of 2 types, prism monochromators and grating monochromators. Grating monochromators are again of 2 types, diffraction grating and holographic grating. And coming lastly to the prism monochromator, the prism monochromator consists of, again as we know the components of a monochromator, it consists of an entrance slit, it consists of a collimating lens, that is plano-convex lens is used, and it consists of prism as a dispersing element. And we have the focusing lenses and the exit slits. We have the focusing lenses and the exit slits. So isolation of different wavelengths in the prism monochromator depends on one important factor. It depends on the refractive index of the material, which is different for radiations of different wavelengths. Okay, it depends upon the refractive index of the materials, which is different for radiations of different wavelengths. So how is this possible? When light from the source is made parallel by using the collimating lens, and if it is made to fall on the prism which acts as a dispersive element,